So, hello all, welcome from all over time zones. So, we have Professor Holger with us in this webinar. So, let me introduce Professor Holger. So, he has retired as the full professor in electrical and electronics engineering from University Duisburg, Essen, Germany, and has worked as deputy director of Fraunhofer Institute for Microelectronic Circuits and Systems, Duisburg, Germany. So his main activities during working life was on CMOS process development, MOEMS process development, and building clean rooms. And currently, he is affiliated with consulting as a senior professor at University Duisburg, Essen, Germany, and he is a lead Ngspice maintainer. So, welcome, Professor Holger. And yeah, over to you.
Yeah, Sumanto, many thanks for your kind introduction. I'm happy to have a chance to give a talk about Ngspice, its current status, and recent developments.
Mhm.
My contents, my introduction. Ngspice Circuit Simulator, what is new? Support for Verilog, analog and mixed signal examples using this support. Xspice code models in Ngspice used from KiCad and eSimM, and with some simulation examples and a few words about what is next. Yeah, why do we want to simulate? Some arguments for emulating electronic circuits by software. Well, you can check the functionality without need for hardware being ready. And it's easy to test variants. You can change devices, you can change resistor values simply, and then resimulate and see what the results might be. And this may save time and cost. You simulate, you verify, and only then you start building. Thus, reduce time and money avoiding redesigns. Okay, some people use automatic circuit generators, and well, you have to cross check. You have to look if these circuit generators have done a good job. So let's resimulate it. Especially in the IC business, integrated circuit business, people do parasitic extraction after layout. And you can also do this on a PCB. And parasitics means parasitic resistors, capacitors, or even inductors. And you can simulate this upfront before you start layouting. And you can simulate then after layout what the result of the actual layout will be. What will it do to your circuit? What I'm currently working on a little bit is reliability simulation, degradation simulation. You can anticipate reliability of your circuit. And this is very important because, for example, space electronics people, they require a lot of anticipation on reliability. Yeah, you also may test entirely new concepts, yeah, without too large an effort. And for me, it has been important. I'm not a circuit designer, but during development of Ngspice, vast learning experience by looking into the circuit. Yeah, if you have an IC, you normally can look only outside on the pins, but with the simulation, you can look into a circuit and understand what the circuit is doing. Yeah, and when we talk about Ngspice, what is it? It's a circuit simulator, and the circuit simulator solves nonlinear time-variant numerical equations. And these equations are used to describe electronic circuits. You see electronic in brackets because you, for example, also could do thermal circuits or even a combination of both. Electronic circuits generate heat, and how to get rid of the heat can also be done with SPICE simulation. And as a result, we get the time-varying voltages and currents. Ngspice is a direct successor of the venerable SPICE 3 from University of California, Berkeley. And Ngspice serves two major purposes or two major groups of customers. On the one hand, it is PCB design support. Ngspice is integrated into KiCad. It's integrated into Eagle and Fusion. It has been used by Altium and some other softwares used for PCB design. Here the requirements are that the user interface should be comfortable, but this is typically via the third-party software. And we have to be compatible to existing spices like pSpice and LTSpice, especially concerning the models. On the other hand, we have IC design support for designing integrated circuits. And here, especially on the new open source PDKs, like the Google Skywater PDK or the Google Global Foundry PDK, and the upcoming IHP PDK we are talking about today. And here other softwares come into play like eSimM, Google Gate IOSIS, eFabless, and a lot of others. Little bit different requirements. We have to be compatible to the well-known CMOS models like BSIM, BSIM 3, BSIM 4, BSIM bulk, BSIM CMG, PSP, and others. In general, compatible to Verilog A models. And here circuits are large. Sometimes people want to simulate circuits with 10,000s of transistors. So we need capability to do that, high speed. And here we want to be a little bit compatible to Hspice PDKs. Yeah, so Ngspice. On the left, you have a circuit, simple circuit, even a German circuit with input and output. It's an inverter. But that's not how you put a circuit into Ngspice. This is how you do it via a netlist. So script-based input, and the script includes including the models to be used, in power supplies, we need the transistors and some simulation commands. So this is the netlist, and this is what is entered into Ngspice. And on the right, you see the output, where the output can be a file, but typically the output here is also graphics. You see the green input curve and the red output curve, and the red output curve is inverted. Well, it's an inverter. Yeah, so far so good. People typically do not like that much entering circuits via netlists. So people want to have graphical user interfaces or GUIs. How to do that? Or why to do that? Well, the netlist as an input quickly becomes confusing, becomes large, becomes reading like a software input deck. And so it's better to have a schematic entry. The schematic entry serves for documentation because it's grouping or visualizing input and output and the devices. And it lowers the barrier for entering simulation in general, especially if you're a beginner, while you would like to have some GUI to put in some transistors, resistors, and so on, and not typing just netlist lines. Well, important thing is, of course, also all the other simulators have a GUI, so we need one ourselves. Okay, Ngspice, we at Ngspice development, we do not develop our own graphical user interface. We rely on partnering with partners. And there are some important ones under active development, and we are in contact or even in cooperation with these people. Open source GUIs like eSimM, which is the main focus on IC design, like QXS, which is a universal interface used for especially RF simulation and also for IC design, like KiCad, which is PCB design and layout, and KiCad offers embedded Ngspice to support the designer, and of course also eSIM with its universal interface, may be used for PCB design, but also for IC design, where it uses KiCad for schematic entry. And here you have some addresses on the web to contact these different GUIs. Well, what's the current status? The current status is the current release of Ngspice is 45.2 from September 9th. New things, we support Verilog A compact device models and analog building blocks. We allow co-simulation with mixed signal Verilog or VHDL digital interfaces using compilers, Verilog compilers like Verilator or Icarus, or VHDL compilers like GHDL. We also can do co-simulation with C-coded digital. And I'm working on degradation simulation, which is stress, simply voltage, current stress, but also radiation. Yeah, how is Ngspice integrated into a GUI? And this is an example of KiCad. We have the simulator, and here the simulator is a share library. So it's not a standalone simulator, it's a DLL or a .so file, and it communicates with eSchema. eSchema is the schematic entry part of KiCad. Here you do schematic entry, you generate a netlist, you send these data, circuit netlist, model parameters, simulation commands to Ngspice. We do the simulation here and send back simulation results. And here we have the graphical representation of the results. If you look at eSIM, it's similar, very similar. A major difference is that here Ngspice as an executable, as a standalone executable is used, not as a shared library. But again, eSIM allows schematic entry via KiCad, integrated KiCad, sends the data to the simulator sends data back, and graphical representation may be done with another Python-based software controlled by the eSIM. Yeah, and this is the interface or the GUI when you use KiCad. This is a circuit, well, it's a simple circuit transistor, RC shift register, so this is an oscillator. And you do the simulation, and you, for example, can do an FFT, fast Fourier transform, and you see here the frequency, and this is the intensity, and here you see, well, this base frequency of the oscillator, and it has its harmonics. It's not a clean sinusoidal signal, as you can see here. Well, and this is just, I think you have started working with eSIM. This is the eSIM interface. Again, a KiCad for circuit entry. Then you do the simulation, and this is the simulation result. The output signal, Vout, is shown here, and this is the venerable LM555 used as an oscillator circuit. Yeah, so I think this project, which is currently going on, there is the idea to design a transistor level or maybe cell level circuits based on the IHP PDK. And the transistors, this is of course IC design work now. And we have to support this PDK with adequate device models. And all these new device models, which are under development or are new today, are no longer written in C code or whatever, but in a language called Verilog A. And so the simulator has to support Verilog A. Well, eSIM bulk is famous for very short circuits, high power devices, gallium nitride devices. Well, and PSP 103, which is the model used by IHP to describe their CMOS transistors, all in Verilog A. And we have to support that. Yeah, how do we do that? We have the Verilog A code for the device model. And Dietmar Warning has made his web page with a lot of Verilog A models. You may have a look at that. We take the PSP model, for example, compile it with a compiler, which is called OpenWAF, into a shared library. And this shared library is then loaded into Ngspice via its OSDI interface. And so we can make use of any Verilog A model which is compilable with OpenWAF. Well, this is just some simulation I did some time ago to verify that things are running. This is a so-called ring oscillator, 19 stages, 19 NAND gates in a series and feedback from the end to the beginning. And this thing starts to oscillate. Well, and it does, and it has its base frequency here at 800 or 600 megahertz, and then it has its third harmonic at 1.8 gigahertz, for example, because it's a rectangular output. Yeah, and the model we have been using here, we have been using the SG13 process, and the model is the PSP 103, and well, so it is working. And here you can have a look at this PDK, or maybe you have got the address already, of course. And here are the other Verilog models. Well, Verilog A can also be used not only for transistor descriptions or capacitor descriptions, but you can generate your own Verilog A devices. And this has been done by Stefan Schippers, the eSimM author. And this is the Verilog A description of an amplifier. Well, and this is the call in Ngspice to call this amplifier. Okay, and this is, well, what you see, the amplifier description. This is, I have to go back. You see the amplifier uses tangent superbolicus. So it is, this is the input voltage, and you see the output is saturating. This is great when output is not limitless, but saturating. And this is the gain versus the input voltage. So you have to be careful to have a good operating point. And the gain is up to 40 for this device. Yeah, you can design that, compile it with OpenWAF, integrate it, load it into Ngspice, and do a simulation. This is the analog part. We have also a digital capability. Digital means you have two simulators, in fact. You have the analog simulator, which is Ngspice. You have a digital simulator. This can be an external simulator like Verilator or iVerilog or DHDL. It can also be the Ngspice integrated Xspice simulator. Of course, if you have digital, which is just 0 and 1 and unknown, and here you have the voltages, you have to translate with DACs and ADCs between the two. And you have a very complex event and time step control. But this is all integrated into Ngspice. Looks a little bit more complex. You have the Verilog code on the far right. You compile it with Verilator into some intermediate C code. You compile it with GCC or the Microsoft compilers into a C code shared library. And this is then loaded via a code model into Ngspice. So if you have digital blocks, you can simulate them together with analog. Digital block is here, analog is here, and this is an intermediate step, and this is fairly automated. We'll see it in a minute. Yeah, well, this is some simulation. This is a successive approximation register, analog to digital converter. The red one is the input, and the yellow one, for each step is, you see that the yellow signal is approximating the red one. And here is the next cycle. You see it just approximating, and it has hit here. Then it may go on to the next cycle. And this is, the approximation is controlled by digital circuit, and the analog part is simulated with the Ngspice thing. And you have just to issue two commands to do this. You compile with Verilator your circuit ADC.V, and this generates an ADC.SIR, and this is then run in a simulation. So relatively simple thing to do a very efficient co-simulation. Well, Carsten Wolf has done this with a D to A converter having current sources, switchable current sources, and this is a counter. The counter is written in Verilog digital, and then these two are simulated together, and you see this, the analog output. When the counter is counting, the analog output is rising. And this is what D to A converter should do. You raise the digital signal and you get a rising analog output. Okay, this is, I can't go into details. You just can look it up. Large, I think Carsten Wolf is very good in explaining things, and even for me, as I'm not a circuit designer, I have understood a little bit of what he did, and so you might look that up. Another example is co-simulation of C-coded things with analog. This looks analog. Yeah? You have switches, you have inductors, resistors, capacitors, and this is a digital part of a microcontroller. Okay, the microcontroller output is on the far right, and the output goes into these switches, in normal and inverted. And either this switch is closed or this switch is closed. And this allows to control the output voltage, to generate an output voltage depending, yeah, on the digital signal. And the control is made that you measure some of these signals here with B sources, and you have, for example, the voltage of the in here, or you have the voltage of V1, this supply, or you have the output voltage measured here, and these signals go into the C code, and the C code has a digital output to control these switches. Yeah, and so you get, you start here, and after some time, the signal is rising, and then you get, at a certain point, a stable output signal. For example, 15-volt output here. And the people, they also did setting up such a thing on breadboard, and this is on the right, you see a measurement with an oscilloscope, and the measured signal looks similar to the simulated. And this is great when reality and simulation are similar. Yeah, so let's talk a little bit about Ngspice. Ngspice addition to the pure analog Ngspice. It is fully integrated. It's old. It's more than 30 years old. So it's integrated into Ngspice since its beginning. It enables co-simulation of analog blocks and digital event-based blocks, and allows also to create a lot of new analog blocks. So both. More than 60 blocks are available within Ngspice distribution already. And the digital simulation is much faster than the analog, factor of 50 or 100. But of course, it lacks waveform details as it is 0 and 1s. The user may create his or her own code models with C code with predefined macros. So yeah, it's a very flexible tool. And it's both supported with KiCad and eSIM. And you can do system simulation with these blocks. And you have the co-simulation capability facilitated by the use of these code models. And the schematic entry may be at block level and maybe combined with Verilog A and Verilog Digital. So you have a very huge capability of doing whatever you want to simulate. This is just the picture of the blocks available directly within KiCad. It's not all of the 60, but the list is growing and directly supported. You just place a symbol onto the canvas and then you can use this device. This is also available in eSIM. This is when you use choose symbol button. You see this window here, and you have eSIM analog, which is the analog uh, code model blocks, and you have eSIM digital, which is digital blocks. And you can use design your circuits. Just a few examples, a very simple example. This is a multiplier. And we multiply two sinusoidal signals. One, the base frequency 100 kilohertz, and the modulating frequency 1 kilohertz. And the result shown here is amplitude modulation. So a very simple thing to just generate amplitude modulation. Well, this is another circuit, a nice audio circuit. The specialty here is 2.5 kilowatt audio. It's not for the private home, I guess, but if you have large festivals or so, you need really power. And this is a digital type of amplifier with digital preprocessing, digital drivers, and an output filter. And here we also have one example why it is good to simulate. If you do something wrong here, the simulator simply says, okay, there is an error. If you build such a circuit and do something wrong, then you might generate a lot of smoke. Yeah. So simulation is very good before you start. Yeah, what is this thing doing? Analog is going in here, and then it starts switching. Either this transistor is on or the other transistor is on. So this is a half bridge. Yeah. And how it is switching? It is switching by a pulse width modulated signal integrated into the audio driver. And you have push-pull, either this one or this one. Never both at the same time on, because this is at minus 100, this is at plus 100 volt. It would be a short circuit with destroying everything. So you need some dead time. This is switched off, and it takes a little bit of time before the other one is switched on. And of course, this one is moving up and down at the higher voltage, and so you need some high side voltage shift. If you want to do this here, well, I started doing this with a net list. But you see, wow, the net list is a little bit complex, difficult to read. And so I think it's a better idea to do this kind of thing with these building blocks I have shown before, either directly in KiCad or with eSIM. You have the PWM, pulse width modulator, here with the analog input. And then you have some buffers. You have the delayed time, the dead time generator. You have these switches, and you have the output drivers, which are doing the high side driving at the same time. And here, so if you look at this, I think it's okay to understand how the circuit is working. If you look at this, it would take a lot of time. So it's good, much better to read and create the netlist by these pre-formatted symbols or circuit blocks. Okay, this is a simulation, and if you look at the green curve, which is the output curve, scale is on the right, up to 5 kilowatt, and if you do the RMS of this, indeed, this amplifier is delivering 2.6 kilowatt at the output. You need huge loudspeakers for doing that. But okay, they are there if you have festival electronics. Last example, analog computing example, so-called Lorentz attractor. Well, these are equations here, differential equations. And you can emulate these equations with the building blocks on the right. And so you can simulate these equations. I think you are too young to to remember analog computers, but they have been in the 70s or 80s of last century, um, where people did analog computation very fast, but of course only uh, percent precise. Yeah, and you can emulate an analog computing thing like this with our digital simulator, but using analog building blocks. Okay, I leave it up to you to figure out how these equations are described by this circuit. What is this circuit doing? Is Lorentz attractor. In fact, this circuit is describing a sort of chaos. Uh, and this is the output, the X output versus, or the Z output versus the X output. And the simulator is somewhere here, and suddenly it jumps to go on here, and it jumps back to go on here. And it's very difficult to predict. Yeah, so people have used these equations uh, just for fun. I like to do this. I have no real application for this, but it just shows that you can describe equations with our simulator, with the building blocks used by eSIM or KiCad. Yeah, so what's next in Ngspice? Some ideas, some more or less fixed plans, some actual activities. We have an ongoing project improving the high frequency capability by adding harmonic balance. And also ongoing is the support for reliability and degradation simulation. We have some plans, hopefully starting in the next year, and we would hire people for this in early 26, hopefully when the funding is available, to simulate transient noise, a very special noise simulation for switched circuits in IC design. We want to test and improve the Verilog VHDL-C interfaces also next year. Always ongoing is improving the graphics interface, especially KiCad people are working on that. We support these building blocks in KiCad schema, maybe in eSIM as well. Well, and the question, if this, I'm not sure if this is a reasonable thing or not, using artificial intelligence for faster model building and simulation. A lot of question marks, but maybe this is coming somewhere in the future. Okay, this is just my last slide. Some links to info and support. And I thank you very much for your for being here and listening and your intentions. Yeah. Okay. Thank you.
Yeah, thank you, Holger, Professor Holger, for this wonderful talk. It was very much insightful to know about the Ngspice, and part of the analog computers was truly fascinating for our generation, the present and the upcoming generations. Yeah. So yeah, thank you. So I would request some of the participants to ask questions over here. So we are fortunate to have Professor Holger here. So I would request you all to ask some questions which you have in your mind, maybe related to IHPDK or some simulation in GSpice or something else.
If there are no questions, not now, but later on, please have a look, for example, at the Ngspice discussion forums. You may ask any kind of question, beginners questions, specialists questions are welcome here. Yeah. So if during your activities right now, next week or next 2 weeks or so, or later on, uh, if they are dedicated to Ngspice, please ask them here. If they are dedicated to eSIM, please ask Sumanto. He might then be or can give better answers on the eSIM. But Ngspice, this is my and our group's task, and we would be happy to answer
There are some
questions.
questions now popping in
Okay,
the chat box. So one of the questions by Harshin is, what, sir, what is the use of LT Spice?
LT.
LT-Spice instead of NG-Spice? Like, how is it different?
Oh, LT-Spice is another simulator. It's a commercial simulator. It's not open source, but it's free, so it doesn't cost money. Yeah, it has a similar application. Yeah, so you can typically you do discrete circuit simulation with LT-Spice. It is not that much or not used in IC design.
Okay, thank you. And there is another question. How does Ngspice calculate the energy consumption or power dissipation in a given circuit?
Yeah, we calculate it by current and voltage. Yeah, you have if you do a transient simulation, for example, you have continuously over time currents and voltages, and you use all the inputs of a device, for example, and measure the currents and have the pin voltages, and then you can do the power dissipation of this device over time. And of course, then you can do some RMS or whatever needed to have a long-term power dissipation simulation.
Okay. Yeah, that's all. Like, is anyone else? Any questions? Okay. Yeah. So I hope they will ask you questions over the Ngspice forum. And yeah. Yeah. So thank you so much for your talk. It was very much insightful. And
Yeah,
oh,
thanks
one more
for
question came again. How
yeah.
does
And
Ngspice integrate device level models to accurately simulate power and energy behavior in MOSFETs?
there is a very interesting thing. If you talk, especially if you talk about discrete MOSFETs, power MOSFETs, yeah, then you have to take power dissipation into account because devices are heating up. And when devices are heating up, they change their parameters, they change their behavior. And this is a feedback loop. Yeah? And we have power device models including self-heating, and we can simulate this feedback loop. So we can simulate real heating of devices. So, for example, you see the 2.5 kilowatt example. I did not check what the power dissipation within such a transistor might be. Well, it's switched, so it is hopefully not too high. But if, for example, for a power device, the dissipation goes higher than 100 watt, then cooling becomes difficult. But you can simulate the all. Well, concerning integrated circuits, is a little bit more tricky because the typical models we have, the PSP model or the BSIM4 model, they don't have self-heating integrated.
Mhm.
So this becomes a little bit more difficult. We can look at these devices from the outside, measure all the four terminals, for example, and then determine the power dissipation. But this is a little bit more tricky, a little bit more effort within the simulator. For the user, it's just typing .probe device, and then you get the power.
So another question, explain how the modified nodal analysis method forms the basis of Ngspice circuit equations.
Yeah, this is the venerable modified nodal analysis. Yeah. So this is we use a very traditional approach. We create the admittance matrix with the modified nodal analysis type, and then use a sparse matrix solver. Or we have another solver which is good for IC design, which is also good for the PSP simulation, which is called KLU. You can switch between the one or the other. Yeah, this is traditional SPICE thing. And if you want to have details, I can recommend you some books or readings to delve into this.
Another question, what are the computational trade-offs between using behavioral models versus device level models in Ngspice simulations?
It's a little bit difficult to answer this question because if you look at, for example, operational amplifiers, commercial devices, you will never get a device level model. These companies always deliver behavioral models because they want to protect their design know-how. Yeah, they will not lay open how they really designed the circuit. So it is difficult to compare. Uh, uh, there have been some older designs, for example, the venerable 741 operational amplifier, 50 years old, where you have both. You have compact, or you have behavioral models, and you have device level models. I think they are comparable. It's not much difference if the behavioral model is good. There are bad behavioral models on the market, yes, but you have to select the good ones.
Then Jay is asking, how does Ngspice compute and visualize power spectral density during noise analysis?
Noise analysis in Ngspice is a small signal noise. Yeah? So you linearize the whole circuit. Even the nonlinear transistors are linearized around their operating point. And then you have a completely linear model. And then you calculate noise for various frequencies. Yeah, and then I don't know the formula. Uh, if you want to have details, I can look up some details on how people did this or how Ngspice is doing this. But you should post your question to the Ngspice forum for details. Yeah.
Then there is another question. Dear sir, I appreciate this talk. Having question, how are the noise and distortion analysis performed in Ngspice? And what mathematical foundations support these simulations?
Yeah, as I said, currently the noise simulation is small signal noise. Yeah. The models, they have noise figures, and it's similar to the small signal AC, except that each device has its noise source, and these noise sources are added up from the entry point to the output, the input to the output, are summed up on the linearized circuit. We want to enhance this also for large signal noise because, of course, for example, if you have switched capacitor circuits, there is no stable operating point, but the operating point is changing with the device because it's switching on and off or switching between levels. And to simulate noise at this stage, it's not yet possible. We just have to see how to do that, and we will start working on this probably next year. There is the capability of doing transient noise. We have noise generators in Ngspice, creating noise voltages, white noise, and you can filter, so you have colored noise, or you even we have generators of 1 over F noise. And you can inject these noise signals into your circuits like any other input, electrical input, and then simulate what the output might be. This is also possible right now. The disadvantage is, of course, if you have noise, you have very, very short time steps only. And this leads to long simulation times. But yeah, that's all you have to pay. So this is possible as well.
Another question from Sandeep. How to compare the computational efficiency of Ngspice and pSpice when simulating large-scale analog or mixed signal circuits?
Yeah, the question, if you ask how to compare, yeah, you have to run simulations. I do not run pSpice. Well, there is a free pSpice TI pSpice which you can download. Perhaps it's available, I don't know. Uh, I never did detailed comparisons. There are people who did comparisons between different simulators, or so-called benchmarking, some benchmark circuits. And there, Ngspice is not too bad. It compares. Because if you look into a simulator, they are very similar inside.
Another question. I would like to know your views on the benefits and challenges of integrating Ngspice into open source EDA tools, EDA flows versus proprietary CAD toolchains.
Yeah, this is ongoing. Yeah. Um, there are we have these PDKs. We have the Skywater PDK, which has been designed by Timothy Edward with Ngspice in mind. So it's compatible to Ngspice, fully compatible. We have the same, I guess, is with the Global Foundries PDK. I didn't use that one up to now. And we have a strong cooperation with IHP, the source of the IHP PDK. And we are using the PDK and Ngspice development. And there is one person, Dietmar Warning from our Ngspice group, who is directly involved in modeling things to keep PDK development and simulator development up to date. Yeah, comparing, and there are especially people are working on analog or mixed signal flows, and hopefully we'll have a larger project next year with a large group of people. We have applied for some money. I think it's a group of 25, 25 research units in Europe to work towards analog flow. And there is, of course, digital flows, digital design flows, where Ngspice is not that important. I think how they're called. I think there is when company eFabless shut down, people were a little bit worrying what is going on, but things are going on, and there will be digital flows as well. Yeah, one has to compare them with commercial flows. One important comparison is the open source flows cost around $0, euros, whereas commercial tools, at least for companies, costs millions of dollars. On the other hand, yeah, there are not that many people working in the open source arena. And this sometimes makes things a little bit difficult, sometimes not that fast. But on the other hand, I can talk about Ngspice. When we get a bug report, typical reaction is within one day. And very often we have found a solution to this problem within very few days. And this, at least people claim, sometimes is difficult with the commercial flows. And well, open source people often do not do that much work on quality assessment because, well, we are like coding, we like develop simulators and GUIs and things, and we don't like too much office jobs. And quality assessment is a very hard office job. But when people ask, we have to look for that. So, well, we are a little bit behind in that. We are, of course, also, we cannot do everything a commercial Ngspice, for example, cannot do everything a commercial simulator can do right now. But I think the most important things are there. And especially when integrated into KiCad, for example, well, people also, companies start using that. Yeah. So we'll see.
Yeah, this is the last question, I guess. So what are the
Okay.
differences between the BSIM models used in Ngspice and those in commercial EDA tools?
Um, in Ngspice, we are using the original models developed by UC Berkeley. Today, these models are published by CMC. I think it's called Compact Modeling Council. Um, okay, and we use these models as soon as they are available. Their Verilog A code is available. We may integrate them into our simulator. Of course, it may happen that commercial, so they are similar, or the starting point is the same. Of course, sometimes commercial companies do extra developments, add some parameters. I don't know. Sometimes we'll see. But of course, what they are doing is not open source, so we don't know the exact details. Sometimes we have to have a look and make our guess, and sometimes we just leave our models as they are. There has been some comparisons with data, Ngspice, and some commercial tools. Unfortunately, commercial vendors strictly forbid to publish such comparison data. Their license does not allow to do comparisons. But I know of some comparisons, and results are very similar.
Okay, one more last question there is. So I am not sure, but I think Ngspice might handle convergence issues differently than commercial tools. How exactly does it manage that?
So let's say the starting point is again very similar.
Mhm.
And what UC Berkeley in the past did was very a very good job. Then, of course, commercial tools may have done some extra developments we don't know about.
Mhm.
Ngspice has done some extra developments, and we, of course, publish it because it's open source. And so things go a little bit, they may differ a little bit. And I cannot tell you the details because I don't know exactly how the commercial tools are working inside. They don't publish it. Um, well, about LT Spice, for example, they published, well, if you look a little bit into detail, simple things like filtering the signals to get rid of, um, um, yeah, to get rid of some transients, or automatically adding resistors. They do it under the hood. The customer doesn't need to care. Well, Ngspice up to now said, well, our customers have to know what they are doing, and when they need extra resistors, they should put them. But sometimes I think it might be good also to do a little bit more work here. Yeah, so there are some tiny details concerning concerning convergence, uh, which can be improved under the hood. Yeah, it's a continuous thing. I'm just in under some discussion with users, with yeah, IHP PDK users, um, designing SRAMs and other large circuits, uh, what we can do. And we will do some things.
Yeah, okay. So thank you, Manojit Kar. So yeah, so thank you, Professor Holger, for being with us and answering all our questions.
Yeah, and many thanks for you listening to my talk, and wish you the nice finishing the marathon and designing good circuits and simulating some of them. Thank you. Bye
Thank
bye.
you. Bye bye.